Hey guys, this is Mr. Sal. We're going to look at simplifying radical expressions. And we do have this product rule for radicals like this. So if I have two radicals with the same index, then I can make it one big radical. Sometimes it works the other way as well. So if I had two factors multiplied together in a radical, I can separate these two into two separate radicals, which we will see. So for the most part in this lesson, it's really going to look like this. We've got to figure out the factors that we're going to take out. Generally, we'll have a perfect square that's going to come out of these, and that's when we can just take that value, which would then just be, for example, if that was a to the power of n, then we would get a times the nth root of b, something like this, okay? Just as an example, right, if I had let's look at the square root of 125. Well, 125 splits up into 25 and 5. Now the reason I got that 25 is because it is a perfect square, which means I could rewrite 125 as 25 times 5. But then I could just separate this into two separate radicals, square root of 25 times the square root of 5. And the square root of 25 is 5. So we end up with 5 times the square root of 5. And we're going to be seeing that a lot in this lesson. So keep that in mind. We're looking for factors of this square root, whatever value it is, and we're looking for perfect squares of that number. Now before we start this lesson and look at some examples, we need to just, again, review the perfect squares, all right? That means if I took, and we'll look at the first 12 perfect squares. So that means if I were to take all these values, 1 through 12, and if I were to square them, then we get values that are perfect squares. So this is a list of all the perfect squares in red right there. So we're looking for these numbers as factors of whatever values we're going to be taking factors of. So on this one it says to simplify the square root of 12. Let's look at using the same method as we did on that last one, but there is another method which we'll look at. So 12, I could split it up into 1 and 12, and the reason I'm showing that is because 1 is a perfect square. 2 and 6, neither of those are perfect squares. But what about 4 and 3? Yeah, that'll work. So the square root of 12 is the same as the square root of 4 times 3, which is the same as the square root of 4 times the square root of 3. And the square root of 4 is 2. So this ends up being 2 times the square root of 3. And that would be our answer in this form, a times the square root of b. Now the good news about this is if we use this method, at the moment we find any perfect square in the list of factor pairs, it's automatically the biggest one that we'll be able to find on these. I guess I should mention that's other than 1, right? So we're kind of skipping 1 in terms of perfect squares. Alright, so for this one, let's take a look at the perfect squares. So there they are on the right. So again, I'm going to look at factor pairs for 405, and of course 1 and 405 works, but we're not really interested in 1 being one of the factor pairs, unless there's no other factors of 405 that are perfect squares. So let's look at some other values, such as 2, no, 3, 3 will work. Let's see what 3 does. So that'd be 3 times 135, but that's not a perfect square, neither of those are. So let's, won't go into 4, but what about 5? That would be 81. So 5 and 81, right? And 81 is a perfect square right there. So I'm going to take the square root, we'll show this a little different, of 5 times 81, which is 405. Then I'm going to split this up, square root of 5 times the square root of 81. And then the square root of 81 is 9. So I've got the square root of 5 times 9. Now be careful on this because we don't usually write it like this in, I guess if we would write it out formally, right? Because it said it wants the a times the square root of b, and a is the 9 in this case. So we're just going to switch these. I've got 9 times the square root of 5. And the reason we can switch those is because of the commutative property of multiplication. So we want all the answers to be like this. Not only that, but if we were to write it, the square root of 5 times 9, sometimes it looks like maybe the 9 was supposed to be in that radical, so maybe we just didn't really extend it far enough. Or maybe even if that multiplication sign is too small, we can't see it. It looks like 59 in that case. So that's why we write it in this form, a times the square root of b. Alright, so let's take a look at this one. 3 times the square root of 135. And we'll use the same method on this one. I'm going to split that 135 up. Let's see, 8, 9. So it's divisible by 3 at least. 3 and 40, 45. Neither of those are perfect squares though, so that's no good. What about 5? That'd be 5 and 27. Still no good. It won't go into 10, but maybe 15 will work. And there we go. I get 15 and 9. 9 is a perfect square of 3 right here. So we have that 3 in the front right there, right? And then it's the square root of 9 times 15. Once again, we'll break that up. So I've got the square root of 3 times the square, let me take that back. It's 3 times the square root of 9 times the square root of 15. And the square root of 9 is 3. So I've got 3 times the square root of 15, and 3 times 3 is 9. So the final answer, 9 times the square root of 15. Alright, for this one we're going to look at it a little bit differently. We're going to take that 27b to the power of 11 and look at its prime factors. Now right away for the b at least, we can change that into 11b's. And we see that all of these are multiplied together. But let's look at that 27. What we're going to do is break this up into its prime factors. So I know 27 is divisible by 3. That'd be 3 and 9, and 3 is prime. And then 9 breaks up into 3 and 3. So 27 we're going to break up into 3 times 3 times 3, and then multiply it by those 11b's. Of course, this is the square root. Now, a square root, it doesn't show the index or the indice there, which is 2. So it means the 2 represents how many we need to make what would be, in this case, a perfect square. That is, if I can find a pair of values that are the same, then I can pull it out as one value outside of the square root. Now, that's just a set of 3's, but how many b's are there, right? There's 1 set, 2, 3, 4, 5 sets of b's that can be pulled out. Now, if we looked at what's happened right here, we've got a 3 here that hasn't been used, so it's going to continue to be a square root of 3, and then this remaining b also would be a square root of b. So I'm just going to move kind of the non-square roots closer together, and then also our 2 square roots, which are also multiplied together. Now the 2 square roots, kind of like we saw at the beginning, I can change this into 1 square root, which does simplify it into a square root of 3b. But not only that, I can take the green 3 here, and then I've got these b's. How many b's are there? Well, they're all being multiplied together, so we got 1, 2, 3, 4, 5 of them. And so I've got 3 times b to the power of 5 times the square root of 3b. And this would be fully simplified the way that we wanted on this one. Again, this is just a little bit different, especially with these pairs now that we have some kind of variable or unknown in this, which is the b in this case. But the 27 split up into 3 times the square root of 3, and then we can also kind of look at those b's separately. So I'm going to do the same thing on this one. I'm going to factor out the g's and w's. So 7 g's and 8 w's. 64, let's go ahead and look at that. So I'm going to break it up into its prime factors. I know it splits up into 8 and 8. Now it doesn't matter which two factors you use here as long as you continue to break it up until you find the prime factor. So I'm looking at 4 and 2 for me, when 2 is prime. And then 4 splits up each into 2 and 2, which are all prime. So 64 is really 6 2's being multiplied together. And of course, this is the square root right here. And since it is a square root, I'm looking for pairs of values, which will then be pulled out of the root. So there's a pair of 2's, another pair of 2's, and another pair of 2's. So those will end up being 2 times 2 times 2. Now the g's, I've got a pair there, there, and there. And then I've got that remaining g, and it has nothing else to pair with, so it's just going to stay as a square root of g. But then also these w's, 1, 2, 3, 4 pairs of w's. So this is what I get on my way to simplifying this. Now I can simplify this right now, some of it at least, by taking 2 times 2 times 2, which is 8. And some of you saw that the square root of 64 is 8, and we've seen that right here. Some of you saw it right here where we were given a pair of 8's as well, and that would work too. But then I've got a bunch of g's right there. That's g's, and I've got 3 of them being multiplied together. Now I'm going to look at these w's. I've got a base w, and there's 4 of them being multiplied together, so that's a power of 4. And then finally the square root of g. Well, this would be the final simplified answer for this expression. So now I kind of want to look at this a little bit differently. Alright, so I'm going to keep that negative 5, of course, but what I want to do is look at just the 150 for now. And I want to split it up into the factor pairs like we did before, because we can still use this method. And looks like, of course, we could use 1 and 150. 2 and 75 doesn't really help us, and neither does 3 and 50. But when we split that up into, let's see, what is that, 6 and 25? And I guess I kind of skipped one there, so that'd be 5 and 30, but that doesn't work. Now the reason I'm looking at the 6 and 25 is because the 25 is a perfect square, which means just the 150 portion of this is going to split up into 5. I'm sorry, that'd be, let's look at it as a square root. That'd be square root of 25 times 6. Well, we could break that up into the square root of 25 times the square root of 6. And then the square root of 25 is 5. So that gives me 5 times the square root of 6. Of course, it's multiplied by this negative 5 from the left here. And we could combine those two also. So negative 5 times 5 is negative 25. So right now I've got negative 25 times the square root of 6. Let's look at the square root of c to the power of 7. Now, there is a different way to do this, but you're going to learn it in Math 1010. So I'm just going to do this the same way that we were doing it before. So I've got c to the power of 7. So I've got 7 c's being multiplied together right here. And if I can find pairs of c's, then I can pull those out of the square root. So that would be a c right there, one right here, and one right here, with the last c still being in the square root because it had nothing to pair it with. So to finalize this, I've got a negative 25. I've got some c's. How many do I have? 3 of them, so c to the power of 3. And it is an exponent because they're all being multiplied together. But then I've got square roots. I've got the square root of 6, and I've got the square root of c. So I kind of skipped a step right there. Hope that wasn't a problem. And this is fully simplified now. Alright, we're going to simplify this radical, except this one is a cube root for us now. which is okay. Let's go ahead and look at that. We'll do it instead of looking for perfect cubes, because those are a little bit even more unfamiliar for most people. So when I split this up into its prime factors, I'm looking for groups of 3 in this case. So 128 looks to me like it splits up into 4 and 32, and then 4 splits up into 2 and 2. 32 splits up into 4 and 8. Sorry, 4 is not a prime, but it does split up into 2 and 2, and then 8 splits up into 4 and 2, and then 4 splits up into 2 and 2. So let's write this whole thing out. Instead of 128, I've got 2 multiplied by itself 7 times. And now I'm just going to look for pairs of 2s. I'm sorry, this is the cube root. So I'm looking for groups of 3. Now, the reason we're looking for groups of 3 is not only because of that index, but groups of 3 will give us a perfect cube in this case. So that pulls out a 2 there. This group of 3 2s pulls out a 2 there. And then this would be 2 times times this other 2, which remains the square root, the cube root of 2. Then 2 times 2 is 4, and then of course we still got this cube root of 2. So this is 4 times the cube root of 2. Now I've separated that. We do need to be careful on this. If I move that 4 closer to that, then it looks like 4 to the power of 3 when it's actually a cube root. So I'm separating it with this multiplication here on purpose. Alright, here's another new index. It's a 4, which means I need a group of 4 of something in order to take it out of this 4th root. So let's look at 80 and its prime factors. I know I can make this 8 and 10, and 8 would be 2 and 4, and 4 would be 2 and 2, and then 10 would be 2 and 5, both of which are prime. So let's rewrite the 80 with its prime factors. And of course that's a 4th root, so I've got 4 times the 4th root of 2 times 2 times 2 times 2 times 5. And now I need a group of 4 of identical factors, which in this case is just that 2. So I've still got the 4 here, and that would be 4 times 2. And then I'm still multiplying this by the 4th root of that 5, because it didn't have 4 sets of anything that it was multiplied with to take it out of that 4th root. Finally, 4 times 2, right here, that gives us 8. So I've got 8 multiplied by the 4th root of 5. And that's it. So here's our last problem. It's another cube root, and we see that negative sometimes, and we start thinking of those square roots, so that we may think this does not have an answer, but it does. And I know right away it's going to be a negative, because I can take a cube root of a negative. 27, let's look at that. We'll split it up. That would be 3 and 27. I'm sorry, 3 and 9 makes 27. And then 9 would be 3 and 3. So this is actually 27. That'd be like taking the cube root of 3 times 3 times 3. So 27 is a perfect cube because it gives me a set of 3 3's for the cube root. So that would just end up being 3. So I've got that negative 3. Then I've got n to the power of 21. Now I'm not going to write all these out. What we need to have understand, hopefully by this time, is the index is kind of like taking the exponent and dividing it by that index, which would make this an n to the power of 7. Now, having done that, divided the 21 by the 3, that takes it out of the root, and it just becomes negative 3 times n to the power of 7. That right there is actually our final and simplified answer.